this lesson today, we're going to be talking about angles and segments within a circle, and that again evolves to open up a brand new area for more theorems and related facts and figures. First of all, we want to accumulate some more terms related to circles and some of their line segments and angles and all. An inscribed angle within a circle is described as an angle whose vertex lies on the circle and its sides are chords within the circle. We call that a chord is a line segment whose endpoints lie on the circle. So again, an inscribed angle is an angle whose vertex lies on the circle and its sides then are chords within the circle. These points, C and B, then are called the intercepts of this angle. B and C are intercepts. I-N-T-E-R-C-E-P-T-S. All right, we have a theorem that opens up about this. The measure of an inscribed angle is equal to 1/2 the measure of its intercepted arc. The measure of an inscribed angle is equal to 1/2 the measure of its intercepted arc. So, for example, what that says, the measure, in this case, of angle BAC is equal to 1/2 the measure of the intercepted arc, the measure of arc BC. So, for example, if this angle up here, let's say, is 50 degrees, then according to this theorem, the measure of this intercepted arc around here would be 100 arc degrees. Now, compare that to a central angle cutting off the same arc. What if this central angle we talked about in the previous lesson cut off the very same arc? Well, remember, a central angle is exactly equal to the measure of its intercepted arc. So if this arc now is 100 arc degrees, that makes its central angle also 100 degrees. So you can see how an inscribed angle can be related then to its central angle like this. Let's review some terms that we want to recall. A tangent is a line that touches the circle at one point. So this is an example. Line TP is a tangent. A secant is a line that passes through from the exterior of the circle through the interior of the circle and on out into the exterior of the circle again. So it's a line that intersects the circle at two different points like this. Now, a secant segment would be just the portion of the secant line from C to D. That portion would be called a secant segment. And then a chord, you recall, is a line segment whose endpoints are on the circle. So these are going to be very important terms to remember as we talk about some of our new properties and theorems today. All right. If two inscribed angles of a circle intercept the same arc or congruent arcs, then the angles are congruent. Let's go back to our drawing here and see how that would work. If we have another inscribed angle in the same circle, 1, let's say, is 60 degrees. Then the measure, if the measure of angle 1 is 60 degrees, then that would be equal to 1/2 the measure of arc AB. So therefore, arc AB would be multiplied by 2 to get 120 arc degrees. So we can go either way, of course. And then if this is 60 degrees, of course, this is 120 degrees down here, its supplement, which makes this major arc around here a total of 240 arc degrees. And that all ties together because in the total circle we have 240 degrees plus 120 arc degrees. That makes a total of 360 degrees. And these two angles, of course, as you can see, are supplementary. If two chords intersect inside of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. Now, the next three theorems can all be tied together. They will seem a little wordy. It may sound a little confusing, but they really make very simple common sense when you see a picture of what they're trying to say. The next three theorems all can be tied together and can be summarized in the same similar way. So, if you don't understand it the first time around, we'll pull it together here at the end. This theorem says that if two chords intersect in a circle, then we'll say this is chord AB and this is chord CD. And we'll call the point of intersection point P. And we're going to try to be consistent with our labeling throughout these next three theorems. According to this theorem, then, the length of this segment times the length of this segment is equal to the product of this segment times that segment. Or in other words, AP times PB is equal to CP times PD. Okay, so that's all it says. If these are two chords, they intersect in a circle, and remember, the center would be down here someplace, we'll say. It's not even where the chords intersect. It's just a general theorem that relates to any chords, whether they pass through the center of the circle or not. Now, the next theorem, if two secants intersect in the exterior of a circle, then the product of the lengths of one secant segment and its external segment is equal to the product of the lengths of the other secant segment and its external segment. There again, that sounds kind of wordy, so you have to read it slowly, read it several times, and let's piece it together. Let's see what this would look like. Let's draw our circle here again, and we have two secant segments which intersect in the exterior of the circle like this. Again, we'll be consistent. We'll call the point of intersection point P. And the points on the circle, we're going to be consistent with our labeling here too, just like the chord was, A and B along one line, and C and D along the other line. Now, let's re-explain the theorem once again. If these are two segments, secant segments, that intersect out here in the exterior of a circle, then the product of the lengths of one secant segment, that would be from A to P. That's the entire secant segment. So we're going to stop it right here at point P because it does say a segment, of course. The product of the length of that secant segment and its external part, the external part would be BP, is equal to the product of the other secant segment times its external part, PD. Okay? That's all that theorem means, you see. So again, it's very simple when you look at it. It's the entire secant segment times its external part only equal to the other entire secant segment times its external part only. Let's go to the next theorem, the third one of the three in this series. If a secant and a tangent intersect in the exterior of a circle, then the product of the lengths of the secant segment and its external segment is equal to the square of the length of the tangent segment. Once again, kind of wordy, but let's make a picture of it and do the best we can. We have a secant segment and a tangent segment. So there's our secant segment, and let's make a tangent segment down here like this. Again, to be consistent where they intersect, we'll call point P. But now, CP and PD are really the same segment. So it becomes, by substitution, just CP, so we square it, because it's times itself in that case. So again, they're all related this way. All right, let's see how this would work then, by using some numbers. If this were 8, and this is 6, and this is 12, and this is the unknown we're going to look for. All right, according to this, then AP, which is 8, times PB, which is 6, would equal CP, which is 12, times PD, which is our unknown x. So 48 equals 12 times x. Dividing both sides by 12, we get x then equals 4. Our missing segment can be found. Let's take a look at an example for the second theorem in this series of 3. Let's let AB equal 8, and BP will be an unknown that we've got to find. And we'll say that CD is known to be 14, and this is 10 in measure. Let's see how this theorem applies and solves for the unknown segment x. AP altogether, you notice, is 8 plus x. So AP is 8 plus x. PB, the external segment, is just plain old x. Down below, we have CP, which altogether is 14 plus 10, or 24, times PD, the external segment, which is 10. All right, now we got to solve this algebraically. By the distributive property here, we'll have x squared plus 8x equals 240. Because it is going to be a second degree or a quadratic equation, we'd have to set it all equal to 0 to solve. So x squared plus 8x minus 240 equals 0. So then we're going to have to factor it down. Prepare to factor. Factors of x squared could only be x and x. Factors of 240, we could try different numbers. We could try 12 and 20 and see how that would work. Those are two factors of 240. Now, if this is negative, so one of these is negative and one of them is positive, the positive would go there, the negative would go there to make this match up. All right, so it does check, so we can go ahead with the problem. And if this times this equals 0, then the idea is then one of these must equal 0 to get a product equal to 0. So we would say in our next step then that x plus 20 equals 0, or therefore x would be a negative 20. Or the other case might be that x minus 12 equals 0, or therefore x equals 12. Two possibilities because it was a second degree equation. Well, x equals a negative 20 has no meaning in this case. It's not practical because there's no way we can have a segment measure that's negative. So x must be the other choice, positive 12. So that's the way you would solve that one. Let's go to an example for our third and last theorem in this sequence. Let's say AB is known to be 10. And let's say this whole thing out here is 16. And this is our unknown right there, the tangent measurement from P to C. Okay, according to this theorem, then A to P, the entire secant segment would be 16. PB, the external part, would have to be then 6, the rest of the 16. CP is unknown, so that's our x, and that is to be squared this time. So this is 96 equals x squared. Therefore, x equals the square root of 96, which is about 9.8 approximately, to the nearest 10th. Okay? Let's try one more that's a little bit different. Sometimes you might run into something like this. If we have a circle, and this is a tangent, whoops, a circle with this tangent out here, which is 2 radical 3 in measure, and this is a secant segment coming down, and this segment is unknown x, and this chord is 4. Again, let's be consistent. The point of intersection is P. This is one single point, so that could be C and or D, and this would be A, and this would be B. Now again, AP times PB is equal to CP times PD. But in this case, C and D are the same point, so this becomes CP squared, because these are the same measurements. So AP altogether is x plus 4. PB is just unknown x, and this square would be 2 radical 3, quantity squared. All right, again, algebraically, we'd solve by the distributive property here. We get x squared plus 4x equals the square of this mixed radical. We'd square each individual factor to get 4 times 3, which is 12. So x squared plus 4x equals 12. Well, once again, you see we have a quadratic equation, so we have to solve it accordingly. So we'd set it equal to 0. Just bring it up here where we have more room. And therefore, x squared plus 4x minus 12 equals 0. And begin to factor. So factors of x squared can only be x and x. Factors of 12 that have a sum or a difference of 4 would be 6 and 2. Again, the 12 is negative, so these number signs would be opposite. The middle term is positive, so it looks like the positive wins out there for the 6. Now, you can check it back to make sure it factors properly, make sure it multiplies back properly, and it does, so we can proceed ahead. So if this quantity times that quantity equals 0, then x plus 6 equals 0, or x minus 2 equals 0. If x plus 6 equals 0, then x is a negative 6 in value. If x minus 2 equals 0, then x equals a positive 2. Well, once again, this really has no meaning. It's just an extraneous root that we'll not check because we're dealing with positive measurements here, so negative 6 cannot work. So therefore, x must equal a positive 2. All right? So these last 3 theorems really can be tied together, you see, by this one simple formula right here. In our next lesson, we're going to talk about the circle as a whole and its parts. So we're going to pull a lot of this stuff together about all the different types of angles and line segments and other related parts, including area and circumference, areas of sectors, and on about several other parts of the circle.